So good day guys. So now we step into the another interesting topic called complement. So a complement is nothing but adding something to make it complete. To make complete. So it's not a compliment. It's complement, right? It's a compliment. It's not like pricing someone you're too beautiful. It's not that compliment. It's a compliment. We are going to add something to make that particular thing to be complete. We'll give you an example, right? So before that, we do have four different complements, right? One's complement, two's complement, nine's complement, and ten's complement, right? So these two, ones and twos, are meant for binary, and these two, nines and tens, are meant for, we can say, decimal or BCD, right? So just remember, complement is adding something to make it complete, right? So we do have ones, twos, nines, and tens complement, and ones and twos meant for binary, nines and tens meant for decimal and BCD. Below I give you a clear picture, a tabular format, so that it will be easy for you to remember, right? So this how the complement methods are ones, right, twos, nines, and tens complement, right? So this ones and twos, as I said earlier, it's meant for binary, and nines and tens is meant for decimal or BCD. Now, while we perform a ones complement, if you are getting the carry, then we have to do a end around carry, right? While we step into the example, it will be clear for you, right? Or else right now we'll look into, right? So ones complement, right? It's just applied for the binary. If you are making the ones complement, and if you are getting an carry 1, then it has to be added end around carry to the LSB bit, right? I'll give you a clear example, right? Before that, we just move on to the one example, like example, right? We have a 101. Now, how to perform the ones complement? Just invert the given bits. So as said earlier, example is 101. So one's complement is inverting the bit. So 1 will become 0, 0 will become 1, and 1 will become 0. So this is the ones complement representation of 101, right? So that carry and all that we used to check while we go for the subtraction. Again, example, suppose we are having a 101, right, and we are having a 011, and we need to perform the subtraction. Now the core important point that you guys have to remember, that any digital circuit, right, any digital circuit will perform subtraction by means of addition. Perform subtraction, right, or just by means of addition. Just remember this, right? Now you can trigger me one question, then why we have learned that binary addition, or why we are going to learn all those binary arithmetic. That is purely for human understanding, but the digital circuit, the computer hardware, will perform subtraction only by means of the addition. Not only the subtraction, multiplication, division, anything, the digital circuit will perform by means of the addition. I hope I do remember we have said the same highlighting statement while we are seeing all those representation, right? So even multiplication, 3 into 2, the 2 will be added 3 times, a kind of thing, right? So the subtraction will be performed by means of the addition. So in order to do that, now consider back the same operation, that 1 0 1 0 1 1. We are just going to perform the minus operation, and we know subtraction will be done by the addition, and for that we'll be using a complement method. And here, as it is a binary number, right, it's a binary digits, we go for the ones or twos complement. So first we check with the ones complement. So the given number 101, always remember, right, this 011, right. I hope this is a just hold on, right. So alright, so in the given number, the 101 is a minuend, and this 011 is a subtrahend, right. Guys, it's a mathematical term, right, just for understanding, right. So we'll be minusing this from this, correct. So this is always said to be the subtrahend, right, because it's having a minus, right, subtrahend, and from this we are doing a minus, right. So consider this is a minuend. This is just a mathematical term, right. Don't want to just overload on it, right. Just understand, for just now to track the statements, right, it will be easy for you. So subtrahend, right, it's a D, right, subtrahend. I think I could write it clearly. Subtrahend, right, subtrahend. Alright, now, so while we do a subtraction, we need a complement technique, and we are going to use a ones or twos complement. First we are going to try with the ones complement. So what we'll do, we have to apply the ones complement to the subtrahend. So now this 011 will become a ones complement as 100. Now what we have to do, we have the minuend 101 and ones complement of the subtrahend, that is 100. So now we'll be performing a normal addition. So 1 plus 0 is nothing but 1, 0 plus 0 is 0, and 1 plus 1 is 0, and we got 1. And this is called carry. It's quite important. Now you have to remember what you have seen over here. When the carry is generated, we have to add the n around carry, means just take the carry and add to the LSB, the rightmost bit. So here we got the carry, this is the LSB. So what we have to do, just take this 001 and the carry to be added over here. For understanding, we just append zeros, right. So now it became a 0, right, the carry will be there, so 1 0. So the equivalent of the 010 binary is the decimal number 2. So this was actually the subtraction result. So this is a 5 decimal number. This is the right ones complement of actually this is right, this is 3, correct. So this is 3. So the ones complement of 3 we got over here is a 4, right. So now after performing the end around carry to be added, right, end around carry to be added, we got the final result. So the result is 2, right. Now we look for the twos complement, right, we look for the twos complement, and again this works only for the binary digits. So now say for an example, we just have a 1001. What's the twos complement representation of this binary bit 1001? So first ones complement representation 0110. Now the twos complement will be adding the 1 at the LSB and getting the result 1 plus 0 0 1 1 0. So the 2's complement representation of the 1001 is the 0110. This is how the 2's complement representation will be happening. Now we go for the subtraction again, because the digital circuit is going to use the complement techniques. Only we go for the subtraction. Now consider we are having 1 0 0, we are having 0 1 0, right? We are going to perform the 2's complement, and this what given sim, right? So if it is a subtraction, we have to use the complement method, and here we are going to use the 2's complement in order to check how it's work. So 1 0 0 is again, it's a minuend, right, for understanding, and 0 1 0, it's a subtraction, right, for understanding. We are going to perform a 2's complement. So 2's complement for which? 2's complement for subtracand. So the 0 1 0, the 1's complement of 0 1 0, right, the 1's complement of 0 1 0 will be 1 0 1. Then 2's complement will be just adding a 1 over here. So 0 1, it became a 1 1 0. So now we got 1 1 0. So add the minuend with the resultant 2's complement 1 1 0. What happened? We got 0, we got 1, we got 0, and the carry is produced. But now, in fact, what is the decimal we got, right? So just for understanding, the decimal what we got over here is a 4, and that's a 2, right? So 4 minus 2, the result should be 2. So now it's an actual minuend. This is 2's complement of our subtracand, and here it became actually 4 2, right? It became like 4 2, right? I hope it's 6, right? It should be 6, right? We got the result as 102, and that is a correct result. But now the carry is there. What we have to do? It's simple. If you are doing a 2's complement or 10's complement, the carry has to be discarded. Just ignore the carry. Just ignore the carry. The carry has to be discarded. Just ignore the carry. But suppose, right, discard the carry, but no carry, right? No, but if there is no carry, now we got the carry, so we are ignoring it. But if we got the carry, then the result would be negative. That we look for another example, so that to you it will be understand, right? So now the result is 2. Simple answer, right? Now we go for a 9's complement. So consider the given number is 5. We need to represent this in the 9's complement. What do you have to do? Just do a, right, 9 minus 5. It's a 4. So 4, right, you can say 4 is the 9's complement representation of 5. Guys, we are just looking on the representation. We haven't get into the subtraction. But first we have to understand the representation. Correct. The same way, 10's complement of 5, right? It's simple. What do you have to do? First we take a 9's complement, that is 9 minus 5 is equal to 4. Then 10's complement is just adding 1 with a 9's complement, so it became a 5. So 10's complement of 5 is 5. You might be wondering, it comes similar, right? But this is just in representation, but we are understanding the process. The real 9's complement, 10's complement will be working with the subtraction. because as I told you, the digital circuit works only with the addition, and addition will be achieved by means of the all those complement. And again, the complement is nothing but adding something, right, to make it complete. So here what we are doing, right, we are adding something in order to make it complete, right. So now go with a very simple example, right. We are having a decimal number like 5, and we are going to do a subtraction, 5 minus 4, right. So now 5 is the minuend, 4 is the subtrahend. So now what we have to do for the 9's complement, we are going to perform. So 9's complement for 4 is 9 minus 4 is equal to 5. It's simple, right? So now we have the minuend is 5, and the 9's complement of 4, that is subtrahend, is 5. Now what we have to do, we'll be doing an addition. It's simple now. We'll be adding a minuend with the 9's complement of the subtrahend. So we'll be just adding it. So what we get? We get 1, 0. Correct. We got the 1, 0. Now the question arises, right? We do got the carry in the 9's complement. If we got the carry, then remember, same as 1's complement. What we have to do? We have to do a end around carry addition. So this carry will be added to the result, right? It became a 1. So the result is 1. So what is our actually sum? It's 5 minus 4. So we got the result as 1. So we are trying to say the subtraction happens by means of the addition, and those addition, it's performed by the process of complements. So for 1's and 9's, we have to look for the carry. If the carry is there, then turn the end around carry to be added with the result, right? If there is no carry, then good. But if there is a carry, then we'll be adding up a 12 less b. And similarly for the 2's complement and 10's complement, we look for the carry. If there is a carry, the carry will be ignored, right? If there is no carry, then it's treated as a negative number. It's quite important. That's why I'm just making you to by heart this particular table, right? So this one is quite important. So 1's complement and 2's complement is used for binary. It's the first one. In both the cases, if we got the carry, if it's a 1's complement, we'll be just adding it to the end around, especially to the LSB we'll be adding. And if there is a no carry, then result is negative. Take 1's complement of the result, and this is the second step what you have to do. If there is a no carries there, then we'll be doing a 1's complement of the result, right? If 2's complement, and again for binary, if there is a carry, then we'll be just discarding the carry, and if there is a no carry, result is negative. So perform the 2's complement of the result to get the magnitude. And again 9's complement, if there is a carry, we'll be adding end around carry. End around carry, if the carry is not there, then the result is negative. So just perform the 9's complement of the result to get the magnitude. And same way around in the 10's complement, if you got the carry, then just discard the carry. If there is no carry, then result is negative. Then take the 10's complement of the result. So this is what the simple understanding for all those complement. Now we go for most important thing, that is sign magnitude. Right, it's quite important. What is sign magnitude? Suppose I'm saying, guys, 5 minus 3, whatever the stuff, the complements, right? You'll say it's going to be the 2. You'll be doing you'll be applying with the 9's complement or 10's complement. You'll be doing an addition to get the result 2. It's quite simple. But suppose if we are having 3 minus 5, now the deal is minus 2. The result is minus 2. Of course, it can be achieved by the complement method by means of an addition to get the subtraction result. But how do we store this minus? That's a bigger question, right? It's very important question. Why? Because how the digital circuit, it's storing the signs, even, right? Not only the subtraction, just take anything, right? Just take anything. Suppose I'm having a -5 to be represented. How it can be represented, right? Suppose I'm having a -100, right? How it's represented? That's a question. We can do a binary equivalent. We can have a binary equivalent for this. We can have a binary equivalent for this. But how the sign will be represented, and that is called the sign bit. So if the sign bit is 1, then it's negative. If it's 0, then it's positive. So the same example, -2. How it's usually represented in binary? Consider a 2-bit representation. It's 1 0. Now there will be one more bit, right? One more bit along with the number equivalent binary representation. This one more bit is meant for sign bit. So now if I have 0, this particular 0 says the sign of the particular digits. So 0 represents positive. So ultimately we have a +2. If same thing, if I'm having a sign bit, I'm having a same number, but now in the sign bit is 1, and again it's a sign bit. Now don't think it's a 3-bit representation and the equivalent 3-bit representation for this is might be a 6, right? But that's not the case. Here the MSB is the sign bit. The sign bit is used to say the sign of the particular representation. Now again we have the 2, but this one represents the minus. So this is how the sign bit will be working on. It's quite important, do remember, and this is called sign magnitude. Now coming back to the complement, in order to how we are handling this sign in the subtraction, especially again the simple example 3 minus 5, we get the answer -2. Now how we are doing the complement method in order to get the result -2? That's the question, right? So first we go with the, yes, it is a decimal, all right? Decimal or BCD, we have to go with the 9s or 10s complement, correct? So we go for the 9s complement. So we got it. This is -n. We know this is subtrahend. Now what I have to do? 9s complement we have to perform, right? So now just make the sign to be apart. Don't confuse the sign over here, right? So just make the sign to be apart over here. Right. So now 9's complement of 5 will be 9 minus 5 is equal to 4. It's simple, right? Now what we do, we have the minuend 3 and 9's complement of the subtrahend is 4, correct? Now we have to do an addition. So no carry is produced. If no carry, what we have to do? We have to do a 9's complement as we have done the nines complement, we have to do a nines complement of the result. What is the nines complement again? So 9 minus 7, and that is going to be the 2. Right. Now the nines complement of the result, right? And once we got the result, as we know there was no carry, then it actually implies it's a negative. So the digital circuit will store the result as negative. So we got the result as minus 2. Now this is how it works, right? It's interesting, right? The only thing, be conscious to do it, right? And same way around, if we go for the tens complement, right? Tens complement, what we have to do? We go for some other example. 4 minus like 7, right? 4 minus 7. So this 4 is minuend, this 7 is subtrahend, and now tens complement of 7 is, first we take a nines complement, it is 9 minus 7 is equal to 2. Right. Now tens complement is just adding 1 with this, so it became a 3. Right. Now minuend is 4 and tens complement is 3. Right. We got the 7, and again we haven't got any carry over here, so which actually implies it's a negative number. Now what we have to do the tens complement for 7. So again, nines complement is 9 minus 7 is 2, and tens complement, adding just 1 over here, so 3. So we do got, right, the result is 3, and as already we know it's negative, the digital circuit will make this as the minus 3. So this is how the complement works with the digital circuit, by doing an addition operation to bring out the subtraction result, and to make the digital circuit to understand and store the minus sign, right? We are seeing the sign magnitude, and how this ones, twos, nines and tens complement, it's handling the minus sign. That's what we have seen. You just remember all those table what we have seen, right, in the beginner. It's quite important, and it's give the ultimate structure for the complements and doing the subtraction, especially for handling the sign magnitude, right? So it's very easy if you understand this. So easy trick to remember: ones complement and nines complement, right? Always have a add, end, around, carry, and twos complement, tens complement. If there is a carry, just discard it. So odd complements like nines, ones, right? Ones and nines, or odd complements. If there is a carry, just add end, around, carry. Just end, around, carry will be added. If it is an even complement, twos and tens, then discard the carry. But same way, if we are having the right ones and nines complement, if you are not having the carry, then its a result is negative. For twos and tens complement, again, if there is no carry, and we have to treat that as a negative. That is quite important over here. It's quite interesting and easy. Just remember this.